comprehensive 3 and 4 are over. And finally 5, it's very simple with it in the end, which is kind of the electronic. Right, so let's start. Okay, so we have this system that has doubles and doubles, so it's a conjugate system. And as we look at this, and again the question says whether the mechanism of the products for the following reaction indicate under which conditions certain products are created, and meaning thermodynamic versus kinetic control. And then we have something to consider. We'll see when it says consider, what I'm going to do, we're going to verbally say how different this is, or how similar it is. Okay, so we have a double bond here, so let's highlight the double bonds.
Sure, can you put the microphone here?
Oh, the microphone. Are all these doors closed there? They're closed and it will be nice and noise. You want
4 hours in total.
Okay, now have it. All right, is that okay? Can you hear? Yes. All right. Okay, so let's. In this conjugated system, let's find the double bonds. Okay, so here's one double bond, and here's the other double bond, and we know that these are the. That's the ones we're going to get. Let's highlight the hydrogen. Okay, so I'm going to write it more clearly here, hydrogen. And the chloride, write it like this. Okay. All right. So now let's see what are the possibilities. I mean, there are 4 possibilities. We know one of them is going to be correct, but let's try all of them and see which we're going to like, right? So if you do this, okay. And I'm going to use this one here too. So there's the red path and the orange path. I'm going to erase some of them, but so that you know. So obviously the red can take place and the orange can take place. Well, let's see what's going to happen with the orange one, right? And so one possibility is to have this, and this, and is to put the hydrogen to the left. Okay, so let's say we have this and then this. Oops, and of course I put something which messed it up. And let's see what happened here. Let's so start all over again because you erased it. So okay. So let's do it one more time. I will do this. And I'm going to do this. And okay, here's the hydrogen. Here's the chloride. All right. So if I attack this way here, I have a choice here. So let's do that. Okay. So the hydrogen can go to the left, and the plus charge will go to the right here. Okay. The other choice is to go to make this, and put the hydrogen over here, and we'll put the plus charge over here. Needless to say, the double bonds do stay there, right? So let's not forget to copy them. So if we do this, I'm just going to use a different color so we can follow it right there. And then this stays over here. Okay? So let's see, if the orange attacks right here, what are the possibilities? Right, we have, some possibilities here, so let's do this possibility here, okay? So, okay, do we all agree this is the four possibilities, right? The red can, attack, the red bond can attack the hydrogen, and can put the hydrogen either here, like here, or can attack hydrogen and put it here and put the plus charge here, yes? The orange can attack the hydrogen and put the hydrogen over here, which is this, or you can put it over here and put the plus charge here. So let's see how we're gonna call these things, right? So this is, let me use laser pointer, and you tell me how to do this. So it's primary, secondary, tertiary. Secondary, allelic, right? It's not just secondary, it's next to a double bond, right? Step, the double bond, that's allelic, secondary. This one here is what?
Secondary.
Just secondary, not allelic, right? Yes? So what about over the other one here, right? That means, so which is, what about this one here? That's secondary, but it's 2 steps away. 1 step, 2 steps, right? So that's just secondary, right? And the last one here, it's secondary, what? Allelic, right? Okay. So this is secondary allelic, and this is secondary allelic, right? You can see here. And which of the two you think would be better? So that's secondary allelic. That's secondary allelic. This is a double bond that's substituted, right? This is a double bond which is substituted, right?
Yeah.
So it's not like anything wins over the other, right?
They're both good.
So we can do both possibilities, yes? So I would call, let's give it some numbers here. This is 1A, 1B. I call this 2A and 2B. And the products of this is like, this is the 1A, and that was the 1B. And I'm gonna call this 2A, and I'm gonna call this 2B. Okay? So that way it'll be easier to refer to them. Alright, so now if we do the 1A, I'm gonna copy nicely. Okay? So the 1A is over here. And the plus charge is over here, right? And obviously the hydrogen is over here, and this is that. I'm just copying the 1A, okay? Right? By the way, I want to let me go back and just put primes because I want the products to have the actual number. It just doesn't really matter. So we're going to call this 1A prime, okay? Right? All right. So we have this. So now, because it's allelic, and why did we choose this, by the way? Because we know what we're going to do now. We're going to do resonance, right? Because the ones we just said is just a secondary. You cannot do resonance here. It's too far to travel to the double bond. This is just a secondary, so those two are not good too far away. But this, which I copied it over here, we can do resonance, and so that's, we can do this resonance here. Okay, and so the product, the result of this resonance is to move the double bond over here. Again, I'm copying the hydrogen. Takes a bit longer to put color, but it's okay for the orientation purpose. Where did the plus charge move? It moved over here, yes? Where the double bond? Okay. All right. So now, of course, we have, what did we lose also in the first step? Loss of Cl. Right, that's so much. So that Cl minus will come back again, right? Okay. So here's the Cl minus. It will come back again and attack this, right? And as a result, we're going to get, you know, the one product here. Okay, so I just copy the backbone, copy the hydrogen here, and now, of course, here we have the chloride in this position here. Okay, so what about if we do the same thing in this pieces here? Okay, and right. Okay, so this one here is going to do the same thing. It's going to come here and attack this. Okay, and as a result, I will get the chloride, I mean the double bond is still here. Okay. And the chloride will be over here. Okay? Alright. And so this is a product, so let me just put this in boxes so we can see them more carefully. Alright. Okay. So I have them 1A prime, 1B prime, 2A prime, 2B prime. Okay. So I'm going to call this different thing. I'm going to call this 1C prime. Okay. And the result of 1A prime is 1A. Then this is going to be 1C. Okay, so I hope I don't repeat any numbers. I have primes, I have no primes. The primes are the intermediates. The no primes is the products, okay? All right. So now, which other one to use? Which other intermediate we're going to use? 2B, right? So let's actually work with this 2B over here. You know, so I'm going to actually let's make it symmetrical. Well, we can work it right here. So here's this 2B. So let's do it over here. Okay. So if we do resonance here, how is it going to be? Like this, right? So the product, this result would be okay. So here's the hydrogen. So I'm copying what does not change, and this double bond will move. So this comes over here. Double bond moves over here, and the plus charge comes over here, right? Okay. And so obviously now the chlorine will come in a similar fashion. Alright? And we're going to do exactly the same thing. So let's try to make the box here so it's nice. Okay. Now for the box you don't like, I don't like it either. Just makes the exam too easy. Okay, so and then we have the chlorine. And then I'm going to have a chlorine over here. Okay, so then this chlorine will come and attack this, and then of course this chlorine will come and attack this. So let's try the product. Let's squeeze it in here. And the double bond is over here, and the chlorine. Okay, so the chlorine comes and attaches right here. Okay, so this was 2B prime. I'm going to call this 2B, right? And then this one, I'm going to call it 2C prime. Okay, that is 2C prime. Okay, do I have I used 2C before? No, right? Yes? No? No. So this will be 2C. Okay, so let's carefully draw this structure here. I need a little bit more space. Okay, so and then the hydrogen's over here, right? And then the double bond here, and then the chlorine should be over here. Okay. Let me double check all my double bonds are there. Okay, please check also if you missed anything. I have extra dots. Alright, peak. So you might be the exam to look for this. Okay, very good. Alright, so we got the products. I have them in those 4 black boxes. First thing I do is are any product the same? Does 1A and 1C is the same? Of course, 1A and 1C is different, have to be. And 2B and 2C are different, they have to be. But let's see if we see any similarities, right? Do we see?
No, they're all different.
The chloro is position 3. I think 1C and 1A is the same. 1A and 1C is the same. I'm thinking aloud now, okay, thinking aloud too. And then we see this, but start thinking about this. Please say yes, but no, say no if it's wrong. Okay. And let's see, 2B is 1, 2, 3, 4. 2, 3, 4. So 2B has the chlorine in the middle. And 2C has the chlorine. Okay, just follow the chlorine. Like, do you agree 2B chlorine is in the middle of the molecule? Like 4, position 4.
Yeah.
2C, the chlorine is position 2, so they're different. There's no question about it. And 1A and 1C, the chlorine is on the 3rd position. Yes. Then you look more carefully. You say, well, that's common, right? Well, and then, so let's take the laser point here. Talk about this. Okay. So in other words, 2B is 1, 2, 3, 4. 1, 2, 3, 4. So the chlorine is on 4 in either direction. And this is 1, 2, so definitely they're different. There's no question. Here's 1, 2, 3. And here's 1, 2, 3. So the same. The rest is just compounds of hydrogen, but the double, right? So it's 1, 2, 3, 4, 5, between the 4th and 5, right? And here is like 1, 2, 3, 4th and 5. Of course, when you name it, you prefer to have this as a priority, right? So it goes 1, 2, 3, 4 is the double bond. Here is 1, 2, 3, 4 is a double bond, so that's true. 5 is the chlorine, 5 is the chlorine. 6 and 7 is. So 1A and 1C is the same, yes? Right? So definitely, right? Identical. So how many products does that create? 3. 1A and 1C is the same. 2B and 2C. Okay. So so you can see this is the same product. Okay. So now the question is, we do the mechanism and the products for the following reaction indicate under which conditions certain products are formed and favored. Also consider what products will be formed if the reactor was growing. So let's talk about in here this little box. Let's make a little, situation, and we say, okay, if a little table, if we have thermodynamic conditions, okay. Meaning, let's say you go to 40, let's say 50 degrees Celsius. I know maybe the lecture was at 40, and I said you don't get stuck with it, just like make it hot. And let's go to the other extreme. You make it kinetic conditions, where you slow down the reaction so the faster will win. And so let's go to, let's say, minus 50 degrees. So I'll put this on purpose because if somebody puts 50, forget the minus, they will say, well, I'm not talking about the same thing, so I must be missing something, so the minus goes to the plus. Okay, and so here, let's see which is going to be the major product. So, let's say that, major product. So what's going to be the major product under thermodynamic conditions? Thermodynamic conditions, you look at the, you look at stability of products. So if you look at those three boxes, remember 1A and 1C is the same, right? And so this is the same. So this is, you look at the double bond. So this double bond, so let's look at the 1A, that doesn't matter, right? 1A has the double bond, has one substituent and another substituent. There's a hydrogen, hydrogen. So this has one substituent and another substituent, that's 2. This one here has 1 and 2, right? Also the same. And here is like 1 and 2, right? So all of them, from the perspective, they're equally good, right? I mean, they're all about the same, so all of them, right? So it's hard to distinguish here, right? Now, if you look at the kinetics, you look at the intermediates. So let's look at intermediates. And so, if you look at the intermediates over here, you look at, this is a secondary and allylic, and that's a secondary allylic, so it doesn't make a difference here. Okay, so this is still good, right? And if you look at the intermediate of this one, I mean the primes, if you look at this prime versus this prime, that's a secondary. I mean, they're of course not allylic, right? And this is secondary, and the allylic next to that has just one substituent. This is secondary, and the allylic here has one substituent. So again, this is secondary, and that's allylic. This is secondary, that's allylic. And the double bond has one substituent, the double bond has, one substituent here. Okay? So what about here? This is the allylic. I'm sorry, here. This is the allylic, has 2 substituents. So here is the same. All right. So to make and so this in this case we're going to make a difference between the kinetic and thermodynamic control. So here's the deal. Yesterday I gave a problem that didn't have 4 boxes, had only 2, right? Because there was only it was really clear. In other words, from the 4 possibilities here, there was only 1 possibility. So their problem was shorter, but they had the kinetic and thermodynamic control. In your problem, you don't have the kinetic and thermodynamic control, but you had more boxes to do. So by doing the 2 problems, we kind of covered our bases, right? So I suggest you do that, and I suggest you do this. Okay? So if you do yesterday's problem, I mean, I told you the logic. You look at the product, look at the intermediates, and then there you can see it's easier in that perspective to see how to distinguish. Any questions on this? Yeah.
What about 1B and 2A?
1B.
It's the one where that you can't stabilize by resonance.
The secondary.
Far away. It's not weak.
1B prime or 1B?
The secondary one, just the secondary.
Yeah, just the secondary without the limit.
Okay, so we're talking about where? This?
Yeah, that one.
That's 1B prime, yeah. But that's not the limit.
I know, but is it a product or does it not?
No, we didn't even make. Okay, well, if we're going to put percentages, to say, you say that's like 33%, 33, I'm just making this up, right? What is not 33 is like 29 or 30. It's like 1% of this, 1% of this. That's why I use major or minor. Okay. So, sure, this is my product, this is my product, this is my product. So really, if you think about it, how many intermediates maximum do you have? I mean, secondary allylic, I mean, these are different. I mean, well, first of all, are these the same? They're not, right? That's secondary 3 carbons from here. This is second carbon. So different, right? So these are 4 different ones, yes? So 1A prime, 2A prime, 1B prime, 2B prime. What about this copy here? 1C prime has the plus over here. It is the plus over here, it's the same thing as this, isn't it? No. 1, 2, 3, 1, 2, 3, and then here. So the 1A prime is the same thing. Well, I mean, it's the same thing. It's just it's symmetrical, but you can also see the same thing because it's resonant, right? Yes. Okay. So you have. So this is not the form, but this is the resonance forms of this, right? The resonance forms. You don't say you have a Euclid line. It's just the resonance. Yes.
So to be correct, we have total of 8 products with stereochemistry.
I was going to ask you. You see, if I asked it, I was done with the last thing. Okay, so I was going to give you half point, so 149. Yes, yes.
Okay.
So very good. No, but no, we don't have 8.
Oh, I'm sorry, 6. So
Six,
one
right.
show one second.
But let's see if they're all chiral centers.
Yeah.
It is. You already checked?
Yeah.
So, yes, yes. So, let's, record this. So, obviously, the last thing I want to say is that obviously here we have the chiral center, right? I mean, I will put it here, but I hope you realize the same, right? Because we said same product. Right? Here is this one here, and then here too, right? Yes. So, really, the major products are 6, right? RNS here, this identical, right? RNS here. So actually, something else. Let's say that you get a product from here which is like 5% of the whole thing. I'm sorry, not this. Let's say you get a product from here 5%. Let's say you make 100 molecules. And this is 5 molecules out of 100, 5 of this, very little. And then this and this gives you 90 molecules because that's the ones they work. 90 molecules, right? 90. So all of this ends up with this. How many products are here?
2.
We have 1, 2, 3, yes? So would this be 30, 30, and 30? No, what? This would be more statistically, right?
Yeah.
Statistically, you have more of this.
Right.
So it might have like 60. I mean, I guess it's not like 60 clear, but it will have more, statistically, be more chances to make this. Okay. So again, that's why we work with major and minor. We just don't try to be nitty-bitty about specifics. Yes.
Won't thermodynamic and kinetic molecules differ because you have a 1,4 product versus a 1,2 product? So
Say
like,
again?
won't 1,2 products favor thermodynamic or favor?
No, don't memorize like 1, because it has to do with the stability. That's what I put on the bottom left corner. That's really what it is. I mean, 1, 2, and 1, 4 is just having a position. But it has to do with where the double bond is. So right here, it's basically how you distinguish it. So in this, you look at the product, and you say the more substitute, the more Zaitsev product is the more stable. So here you have double bond, you have 1 substituent, 2 substituents, and 2 hydrogens. So same thing here, 2 hydrogens, 2 substituents. I mean, this is identical. Here's 1 substituent, 1 substituent, and here's 1 substituent. So from our perspective, thermodynamically, it doesn't make a difference. Now, if somebody might argue, wait a minute, I mean, there's a chlorine here, adaptive effect, the chlorine is on this side. This is, an ethyl group. So again, if you're going to be nitty-bitty, that's when we don't get 30s and 60s, right? You get, if you put all the parameters together and you do molecular modeling, you might come close to the reference. And so the other clean answer is, if you look at the kinetic product, you look at the activation energy, which has to do with the intermediates, right? And intermediates, you look at these guys here, right? Which is more stable, right? So obviously we didn't even bother with these things because we said this is secondary, that's secondary. And, that's even higher in energy, right? You want with lower energies, lower activation energies. So again, I designed this problem so if between the Tuesday and the Wednesday, here's a possibility that you don't have a kinetic and choice. Yesterday you do, but here you have more intermediates than you had yesterday, right? So it's kind of, different angles of looking at the same problem. Any questions? Okay. All right. Tell me, I cannot go back. Okay, huh? Oh, yeah, the question is what if Cl2 attacks? Well, all you have to do is whatever I put the hydrogen, remember I had the red line with an H? Well, just erase that H and put a CL. So that's an extra practice, right? You go home and just put a CL instead of HCL, you have CL. So red line H, red line, CL. And then Carl Sanders would be more.
Yeah,
so
that would be
different. But mechanism, the whole thing would be very similar. Huh? Yeah, I mean that's what I said. They have to do stereochemistry, anti, and well, they want two by the end. They want four. It's different story.
It'll form a triangle with the CL2 when you. So it'll have to be a bottom attack.
Yeah, if you do so, the 1-2 product forms a triangle, right? The
So can you
140 creates a plus that will come back.
Can you have resonance with the triangle also, or you leave the triangle as it is?
No.
You don't
no.
touch the triangle.
So the 1-2 is just regular CL2. But the 1-4, you will have a couple of advantage. So again, I'm asking the question, the CL2 is going to be about 89% the same problem, so you have to think about the stereochemistry, you have to think about if it's a 1-2 like the anti, right? So the stereochemistry will be slightly different when it comes to the chloride. Yes?
1A and 1C wouldn't be the same then, right?
Yeah. So yeah, so if you want the answer to this question, just copy my answer and just erase the H to the CL. And then think about how different, now you may have 4 products to for it, right? Yes. Is that, I don't look at the problem, but I know what you're saying, right? Because so here, let's summarize it. If you use CL2, you just replace the blue H that I had in my drawing there with a CL, and think about if you narrow down to if the 2 products are the same or now they're different. So maybe there are 4 boxes, 4 products instead of 3, yes? And also think about the stereochemistry, like the anti you're saying, so. Any other issues? Okay, so let's go to the more serious problem, right? And, okay, so this is the Diels-Alder.
That's from this one? No, this is the resonance of this. This one exists. No, but this wouldn't exist because you said there's no resonance of the triangle. So this is only possible because this is the resonance of this. If you do the triangle, you can't have resonance, so this one exists.
And so we don't like it?
No.
So we just
No, at first CL, you're still right now, the CL comes in, you form a triangle. You can't do resonance
I mean,
anymore
just
now.
But he just said that these would be the same products that you would have for going.
any other issues or questions?
Because he said he can't do resonance to give the triangle.
So let's see.
Right? Is that? I know. Don't it make sense? Like, yeah, that's what I was gonna say.
It's easier for me if I face this.
Just scratch my fur. I'm ready to go to war right now. About to get this. Gotta get that bread. No ace. No ace.
What is the condition here? This is so draw the mechanism of the products for the following Diels-Alder reaction, including the correct stereochemistry reaction, and then draw the transition state as well as the orbitals which are involved. Also explain how the HOMO and the LUMO orbitals make this reaction thermally allowed. Right. So, first of all, we need to recognize which is the diene and what is the dienophile. Okay? So is it fair enough to say that this is the diene?
Yeah.
Because it's double, single, double, but somebody would say, wait a minute, this is double, single, double. Actually, in some harder problems, you can see that this actually can work as a diene. And, you get, so I'm going to say early on, close the parenthesis, that you can have this double, single, double react with a double bond. But obviously this is this works as an electron what? Withdrawing group, right? So let's actually use 4 different colors to understand what's happening here. Well, I'm going to use red to identify the diene, okay? And I'm going to use green to identify the the dienophile, right? So that's the dienophile. Okay, and then this is the diene. So you just looking at those colors, that's all you need to do the reaction, the red and the green. Now, what is this group here?
Substituent.
This is the
Donate.
donating group. And what is the other part that we have over there?
Withdrawing.
Right? This is the withdrawing. Okay, we use all the basic colors. Maybe we can use them stand out. I think purple would stand out, right? So we can. Okay. So this is the what? Electron withdrawing group. Okay, so step back and pause on this because this is the basics, right? The basic is the red versus the green. The red has how many carbons? 4. The green has how many carbons? 2. 4 plus 2, cycloaddition, that's the basics of build-up, right? And if it was the red and the green, we just finish it because they're symmetrical, there is no endo rule, there is no wedges and dashes, there is no up and down, no stoichiometry, right? But by putting the blue and the purple, you have some orientation, or you have left and right and so forth. But not only this, because you make something more rich, you make the red backbone more rich because you donate, and you make the green backbone more poor because you're withdrawing it. So that's what you want. Parenthesis, what would happen if I switch the blue and the purple? The answer is multiple choice question?
No reaction.
No reaction. Right? Because you want the red to be rich and you want this to be poor. So if you put the purple here and the blue here, there will be no reaction. Very easy. Thank you. All right. So now the other problem is now for this to take place, you know that the red is not in the right place because this is S what? Trans, right? Meaning the two double bonds are facing away from each other, right? So you need to kind of rotate the bonds, rotate around this bond, and if you rotate around this bond, what are you gonna make? It's gonna become like this, right? And so hope without showing you any plastic models, you agree that the little black arrow I did over here, it gave me this, yes? Everything, I freeze this, I don't do anything right here. You just flip this around here, I rotate it, and it comes over here. So now it's what? S? It's S6, yes? Alright, the other one is just position fine, there is nothing we can do there. Now, the question is, we need to know, so we're going to do some work here to position these things in the right place, okay? To see, how the attack will take place. For example, if you, so for example, would this double bond attack or this double bond attack? Here's the question mark, right? Right, so you don't know which, you can memorize it, but we're going to do some resonance work here to see which one will attack, which of the two red arrows works. Okay. So the way to do it here, we're going to take this over here, and let's actually work it over here, have more space. Okay, and here's the blue one over here. That's the same molecule, I just put it like this. And now, this is electron donating group. This blue one is electron donating. And it's electron donating through the inductive effect. So electron nest is moving this way, this way, this way, this way, this way, this way. But it's really hard to see it when you use the inductive effect. What you're going to do now is you're going to, so to speak, cheat and take this blue line and put an oxygen here. That's just my suggestion. Right? The books don't say this, but So I'm going to make an oxygen because now it's the same ethyl group, it's just stronger, yes? Right? It's electrodynamic, but now you can use resonance to help you guide it. And then again, just go and erase it, right? Or after do the scratch work, then we can find the orientation and use it. Okay, so let's do some resonance. So you take one of these lone pairs, and again, let's do it more properly. So I need to make it a little bit longer, so you can see this, right? And then just like this. Okay. So let's have this. So you take this and you put it down here. And here's the issue. Can I do this? No? Okay, because you break the bone, right? There is not, can I do this? No. Can I do this? That's the only thing I can do, right? Yes. Okay. So that's what I'm going to do is, so let's write the resonance structure. And again, please pay attention here because your book doesn't show this so-called 1, 2, 1, 4 products and how this works and so forth. So that's why I'm going a bit slowly here. Okay, so right here you create a double bond, a plus charge, it stays, right? And then what happened here, you have a lone pair over here, right? Yes. So this tells me this is the nucleophilic carbon, yes? Okay, by the way, what will help is the following. So let me go back a little bit and do the following. I call this number 1, 2, 3, 4. So to Orianderson's, right? This is number 1, 2, 3, 4. Okay, this is number 1, 2, 3, 4. And that's number 1, 2, 3, 4. Okay, so with all this work, I mean, I did this 4 times, like the same structure, it tells me which carbon is the nucleophilic. Which is the one that's going to donate these electrons? Number 1, right here, right? That's where it's going to start, right? And so this is the scratch paper work. Okay, so let's take this molecule now and work on this. By the way, this is resonance. Okay. So if you take this one here and you take this molecule right here. Alright, so I'm copying the other molecule now. Alright, and now we let's do resonance here. So obviously this is going this way, and what else happens? The green one here is going to come this way, right? So the resonance of this, and by the way, let's do the same thing here. This is number 1. Let's not do 1, 2, 3, 4 green ones and red ones. Let's call it different. Let's use 5 and 6. Because Diels-Alder is about having 4 carbons, red, and 2 green carbons making what? 6 carbons, right? Yes. Again, very important when I do 1, 2, 3, 4, 5, 6, this is not to do with nomenclature, right? Because if you do nomenclature, you get priority to this group. Call it A, B, C, D, E, F if you're confused, right? Or put smiles or crying face or whatever. Just as long as you make them different, right? Okay. So let's call it 5 and 6. And this is the 5 and 6. And according to this, this is the green one here. Here is the okay, this is that, and now this is 5, and that's 6. So what is the charge, by the way, what is something important here? What is the charge over here? 0. What is the charge here minus? The whole thing must be 0, so if this is minus, where's the plus?
6.
On carbon 6, there is a plus, right? Same thing on the left, right? I mean, this is 0, 0, 0, 0, but now here's a minus, here's a plus, right? The total is 0. Which is the more stable resonance, the bottom or the top? Top. What's the most stable? Top. That's the one we're going to use. This is our scratch paper, meaning, I don't try for a better word, that's our work area, which I need to see if there is an exam, right? I mean, it's not scratch paper, I need to see. Actually, I take that back in a way, I mean, really we cheated here, right? Because we need to see this, but this is not really the real molecule. Right? But it's nice to show how we figured it out because the oxygen is not there. But it tells me the oxygen helping by resonance to figure out where is the nucleophilic carbon. So what's the conclusion of all this work? That carbon 1 will attack what?
Carbon 6.
So carbon 1 will attack the 6. The minus will attack the plus, yes? Again, you will say, what about the blue oxygen? That's a plus. And then what about this one? Do they connect? First of all, oxygen bond very weak. But remember, the chemistry is between the red and the green. The blue and the purple, they're substituents. They're just helping. You understand, right? So we have two pluses and two minuses, but it's the red plus, the red minus attacking the green plus. Because the delta is red against green. Okay. So after we did all this scratch paper work or work area, now we're ready to just put it nicely and position properly and so forth. Okay. So we're going to take this molecule here, and position it in the right way. Now, of course, these are not positioned properly, right? I mean, this is not, the 1 and the 6 are not positioned the right way. So either I'm going to flip this or I'm going to flip this, okay? This is a bigger molecule, just, keep it, in the right place. So let's take this molecule and put it over here, okay? So from this step, we're going to work over here. Okay, so I'm going to take this molecule nicely, put it over here, okay? And now I put the blue one. Should I put an oxygen now?
No.
No, right? Because the oxygen was there just to help me figure out what's happening, right? Okay, all right, so this is the original molecule that was given to me, right? This is it, right? Double, single, double, red. Here it is, but I flipped it. It's SC instead of S trans. Here's the the blue donate substitutes right here. Okay, let's position now this. Should I position it like this? And here's the interesting part that you have to. Right now I'm doing something which is going to review two principles. Is this correct? No, because I'm going to write things and erase things, okay? Because I don't have enough space. So if I do this, by the way, this is 1, this is 2, this is 3, and this is 4. And then this is 5, and then this is 6. If I did this has to come over here. The 1 attacks the 6. I want the 6 to be close to the 1, right? So I need to flip it, right? So that's one thing. So I'm going to flip the 5 and the 6. And what else? Okay, so let's do that. We'll do this one at a time since we're recording this. So I go like this. So here's the green one. Okay. Right. And so now I have this here. So now the 6 is over here and the 5 is over here. I just flip it, so now the 1 is very close to the 6, yes? So that takes care of all the resonance thing. This takes care of the 1-2 versus 1-4 product and not of the 1-3. You cannot do a 1-3 product. Okay. So one more thing here which we need to, so obviously this is, take this out, because now this is ready to do this kind of attack, right? Yes? Actually, the reason I don't go from 1 to 6, I go from the double bond between the 1 and 2 because that's the extra electrons, yes? Now, there is something else we need to adjust slightly. The endo rule. The endo rule says the purple has stickiness, right? Because it has all these balloons, right? And this stickiness wanted to be, this is the key word, auxiliary, right? Supplementary, helping, giving an extra, help here. So you want this to be facing this way. So not only we took this molecule and we flip it north to south. You agree this is north-south, this is south-north, yes? And now we're going to take the purple and make it, left to right, right? We're going to put it over here. So I'm going to erase this. Right? And okay, this is still 5, just put it a bit above 5 here. Okay? And then I'm going to put the purple facing
The negative charge.
facing
Flip it towards the
diene, yes?
because you want both.
Correct?
Right?
Right? So now, by taking that molecule and flipping north to south, so to speak, and putting left to right, I satisfied what the resonance told me, how they need to be aligned, the electrodonating and the group, and also the endo rule. Okay. And so now, after you do this, so a lot of work is how to position the molecules. So then, it's very simple, right? So now we did the first arrow. What is the second arrow? What color does the second arrow have? Green. So it goes between the 5 and 6 to where? Here, to make the bond, right? And then what's the next arrow? Right, between here and here. So that's the 3 arrows with it. Oops, yeah. And, okay. All right. With my laser pointer, let me ask this question. Can I do this? This is going clockwise, right? These arrows, right? Can I go, from here to here, from green to here, and from here to here? No. Right? Because then might be, it sees the same thing, the same result, but no, the flow of arrows is very crucial. Right? That's worth a lot of points, so to speak, because putting the arrows this way, was due to all this work with it. So is this a transition state? No. Transition state, of course, if you do this, then to do the transition state, it's only if you forget it, and if you hit your head, I forgot it, that's easy points, right? Because now it's, So let's do the transition state, which actually we don't do it for all the experiments, for all the, but this is a good place to do it. You have to write very carefully here. Let me just take the microphone aside, because I'm afraid I will push the next button and then it's going to erase the whole thing. Okay, so let me do this. Okay, so now let's do the transition state. Has to do with breaking and forming. What happens between the 1 and 2? Again, let's put the numbers 1, 2, just a second, 3, and 4, and 5, 6. Okay. Okay. So what happens between the 1 and 2? Breaking or forming? Breaking, right? What happens between the 1 and 6? Forming between the 6 and 5? Breaking is then between the 5 and 4, obviously what? Forming, and then 3 and 4. Breaking, and then 2 and 3 form. Okay? And again, the transition, look, don't get confused, because sometimes I will ask this in exam. This is the intention. This is like where it's going to go. So the beginning of an arrow is breaking, the end of an arrow is forming. Yes? Right? So technically, look, sometimes if you put this arrow over here, that's when you combine transitions. If you put the arrow over here, then you have to put a dotted line. That's where it's going to go. But it's more correct to say this: those two dots are coming and attaching to this carbon, and that's what they make a new bond. So the combination of this does the picture much nicer. All right, so that's the transition state. And then the next question is what? What is the final product? Right? It's for stoichemistry. We do stoichemistry. Okay. So the product then of this obviously is right here. So we just do the bucket ball, right? And here we have the new double bond, right? So this is 1, and this is 2, 3, and 4. So here's the electrodonating group. We created a new bond over here. Oops, see, I was afraid about this. Okay, so why did they have this? Okay, so let's have a look at that. Okay. And save. Okay. So let's do this. Go over here. So I want to save this in the if I talk about this slide, it will erase it. So I'm going to go to the next slide and continue there. That's why this extra slides. Okay, so let me continue this area here. Okay, so I need to remember the molecule. I'm just going to write something here, right? So it was like this, right? Yes. There was a blue line over here. It was this. It was over here, right?
Yeah.
It was this. See if you can give me a grade now. Don't tell me. It was this.
Yeah.
This was over here, yes?
Yeah.
And this, yes? No? How did it look like?
The,
was inside.
had another carbon attached to it.
Was another carbon?
Yeah. Then had another carbon and oxygen attached to the second carbon.
Yeah, just went up.
There's two carbons.
It's carbon and then there's another one. Right? This is it, right? Yes?
The CH3 is inside.
Yeah, but we need to wedges and dashes yet, yes? No?
Yeah, I was gonna say it doesn't matter how you put the withdrawing group because it depends on when you're attacking from the top.
Well,
or
now
bottom.
the stereochemistry will explain it, right? Okay, so so if I wanted to do it the actual, I mean, if we do the opposite, we like this. You will do it this way, right? So, you want the oxygen, you have the p orbitals to be facing towards the red side, yes? And we'll see much more clearly when we start putting wedges and dashes, okay? Okay, because even that it's like a rotation, but when I put wedges and dashes will become more clear. All right, and so this is the molecule, all right, this is the product. And now we need to put, do I have any chiral centers here?
Yes.
Here's the chiral center, right? Yes. Right? Now, do I have a chiral center over here? No. So, if you have a substituent on the second or the third carbon, it's not an issue. If you go to the previous slide, this blue was on the double bond. The double bond used to be here, so it was not an issue of chirality. And here's on the double bond. So the blue one, when it's between the 2 and the 3, that makes the stereochemistry simpler in terms of the blue. But then, of course, this is the star, and you have to have the two substituents. So let's see what are the substituents. So if the attack happened from what?
Bottom.
From bottom, and I would suggest you do the attack from the bottom, then this would have been like this. Okay? This is a dash, right? Okay, and then of course this doesn't matter. And if the attack happened from, technically speaking, when I say attack, the attack was from the previous structures, right? Okay? Which is the previous slide, okay? And if the attack happened from the top, then then you have this, and the green one here, then this is going to be a wedge. Okay? And then blue is not. So, one thing I want you to pay attention is this. If the attack is from the bottom, this is a dash. If it's from the top, this is a wedge. This will never change. Okay? So I suggest to always, first do the attack from the bottom, put the purple one as a dash, and that satisfies the end rule. And by having satisfied the rule, if somebody else from the top, it's going to be exactly the opposite, right? Okay, but let me say one thing. So the one on Tuesday, I gave him another problem where the blue, the donating group was on position 1, and their problem was a little bit more busy because then you have chorality there. You have to think about it. But if you don't do this problem, which I suggest you do, let me tell you a few things because this is a bit easier, right? So that's a bit more difficult. So let me tell you the punchline of this. At least I'm going to repeat one common theme to understand because that's really very tricky territory. So to understand the chorality, let's go. What if the blue one was on position 1? But in order to understand this concept, let's do this problem here. You have. So let's see. What if the donating group the donating group was on position 1,4. So this is what I'm talking about. So if you have this, is this S6 or there strands? Cis. Okay. So what about if this group was here? Yes? That's what I'm talking about, position 1, right? Yes. And in order to study this, a good model to use is not to do this, but to do this. Right? Okay, so this is like having two donating groups, so position 1 and 4. Right? 1 and 4 is the same kind of idea as having the 2 and 3. So today's problem, do you agree in today's problem, what was the blue group? On position 2, yes? Do you agree this was on position 2? I'm going to put it on 3, that's the same idea, right? 2 or 3 is meaning the middle, right? So if you want to practice at home, do a 3 and see, whether you need to flip the molecule or not. So that's the suggestion. So what do you put it? So let me do it one more time here. Let me gently here. So this is position 1. That's what I'm going to ask. Yeah, that's hard to really see what's happening. And then position 4. So let me erase this. So I agree, either 1 or 4 is the same idea. Yes? Let's put them on both. So here's another molecule. And let me do this molecule, which is used in a lot of homeworks and is good for studying these reactions. We do this molecule because it's like having two methyl groups, except they're tied together, as one unit. Right? So if you have this kind of situation, and then this molecule comes and attacks with a carbonyl over here, or the carbonyl over here, left or right? Left, right? So you said this is not good, right? So you do like this. And we say now, we all agree, attack from the bottom. And of course, nobody says that we will not ask you from the top or even exam stuff, but let's say, if you do the plastic models, you understand, if you attack it from the bottom, we don't change this, then, this, you will understand it when I do the backbone here. Here's the solid backbone. Here's 1, here's 2, and here's 3 and 4. What is between 2 and 3? The double bond, right? That's how Diels-Alder works, right? The 1 and 2 and the 3 and 4 has gone and is replaced by double bond between 2 and 3. We must know this. Yes? We did this with the numbers, right? So, do you agree if something attacks it from the bottom, this blue thing kicks up? Yes? Something gives it a punch from the bottom, the bottom there, right? So then this is what you have. I'm sorry, actually, technically, this is a green line, right? Yes? And so this is the other molecule, right? I mean, let's do actually, you in order to understand the attack, this is this. So, let's put numbers. This is 6, I think we said, right? This is 5. If we want to keep the same numbers as before, is that true? or 5 and 6. That's 6 and 5, right? Yes, okay. All right, and so between the 5 and 6, what happened? This. So do you agree between my red 4 and the green 5? That makes sense, right? Because of the attack? You agree this connecting 5 and 4, just like this, that's why it's green. And then what happened between 3 and 4? It went between 2 and 3. Right? That's the mechanism of this. So the question now is, where does the purple thing, where is the purple thing? Okay. Okay, so is it this? Is it, just a second now. Is it A or is it B? A, right? A, that's the two choices. You agree there are A or B choices? One is wrong, the other is correct. It's A, right? It has to be underneath, and the sticky side of the purple carbonyl should be underneath the red one. That's the Ando rule, yes? So let me erase that. Okay? And so, and when you do this, and if you want to now put wedges and dashes, so now you can see it here with solid lines. But if you want to put wedges and dashes, here it is. This is a wedge here. Right? If you use the hexagon as your surface, so to speak, like the red and the green, if you take the red and green lines and consider it as a surface, right? The flatness, that blue is a wedge, yes? And so that's a wedge. And then according to this backbone, this is like a dash, right? Okay? So, because you can see it better now. Now, you say, wait a minute, if this is the case, then how about if this was like this? Like this. You see I erased that blue and I made two methyl groups? It's the same structure, isn't it? The same construction, yes? I just took my white out and I made that CH3 into CH3, right? So all I have to do is what? It's the same idea, except that, I'm sorry, this is blue. So it's the same idea, except they're not connected, yes? So I just want to show you structure how these wedges are coming from, right? So they're connected. So to make a long story short, here's the thing. If donating groups are facing in, right? Meaning this, then the product will be shown as what? As wedges. Okay? If the ring will be shown as wedges. Okay? And if the donating groups are facing out, what do I mean by out? And this is harder to see because it's harder to really to grasp this because that's why I use the ink because it's easier to see like a little envelope pointing up. Then it must be the opposite, right? Okay. Then at the product will be what? The product will be shown as what? Dashes. Right? Okay? But all of this is a big assumption, right? Assuming that attack is from where?
Bottom.
Is from bottom. Okay? So that's important. So that's the headline, right? It's attack from the bottom. And then the withdrawing group will be what? Will be a dash. Okay, so to put everything together, before you even talk about any of these things, you say, let's agree all, we're going to do attack from the bottom. So if you attack from the bottom, the purple electron withdrawing group will be a dash. Right? Bottom electron withdrawing dash. They go together, that's one phrase. Then, the dominating group, if it's position 1 and 4, yes? That's Tuesday's problem, right? You know, today's problem was 2 and 3 was not an issue. Then, if it's inside, facing in, is going to be wedges. If it's outside, it's a dash. What about if one is in and the other is out? One is a dash and the other is a wedge, yes?
That's normal.
And there are 4 possibilities, right? You know, dash, dash, right? Wedge, wedge. And you get So now, what happens if everything is from the if the attack is from the top? It's going to be exactly the opposite. Right? So let's do it. Assuming the attack is from the top, the withdrawing group will be wedge. If these things are facing in, there will be dashes. If it's out, it will be wedges. Right? So you can see something has 4 possibilities. We can just simplify it like this. Yes, question?
I answered it.
Huh?
I got it.
I didn't even finish talking. You feel the vibes? You get the vibes? Yes.
How would you show that the wedges?
Huh?
If it's an attack from the bottom, how would you show the wedges in a molecular model here? Like,
You mean the computer thing?
yeah, no, like through a kit and a kit, like plastic models. How would you show it?
Yeah, I mean, the
How would
plastic
it be?
models, yeah, so the plastic, again, did I give it? Yeah, that's a good time to list the plastic models. Let me see, because I should have So, I hope you realize we go slow here because that's like half the unit, right? I mean, or more than half the unit, like everything's here. There's resonance here, donating groups, from transition states, the others will be faster, I promise, right? Okay, so